Hello and welcome to our series on abstract algebra. This is going to be the first in a series of videos that will cover the basics of abstract algebra, including rings, fields, and groups. But we're going to start with rings, and the definition of rings will be the subject of today's video. So I've written out the definition of a ring here. Okay, so we'll just go through it, and as we're going through it, we'll look at a classic example of a ring, namely the set of integers, and we'll show side by side how the integers satisfies all of the definitional requirements of a ring. Okay, so to start off with, a ring, which we'll call R, is a non-empty set. Okay, that just means it has to have something in it. It can't be completely empty. With multiplication and addition, so this just means that you have to, there are two operations that you can do to the elements of this set, right? And usually they're thought of as addition and multiplication. We'll treat them that way for now, which satisfies the following axioms. Okay, so all 8 of these have to be satisfied by the set in order for it to be a ring. Okay, the first one is called closure under addition. This just says if you have, if A is an element in the ring, or in R, and B is an element in R, then the sum A plus B must also be in R. Okay, so the idea here is you cannot escape from the ring through addition. You cannot take 2 elements of the ring and add them together and get outside the ring. All right, so as we're going through this, we'll see how the integers satisfies these, right? So for the integers, right, if you just take any 2 integers, say 3 plus 5, in this case we'd get 8, right? Now, I've just taken a specific example here of 2 numbers, but you can in fact prove that for any 2 integers you pick, this will be the case. You will always get an integer if you take 2 integers and add them. Okay, so you can't escape from the integers by adding 2 integers. All right, so the integer satisfies closure under addition. The second condition here should be familiar from high school algebra. This is called the associative property of addition, right? It just means that if we are adding 3 things, it doesn't matter whether we add the second 2 first or the first 2 first, right? The integers pretty clearly satisfies this, right? You can test this out with numbers again just to convince yourself, but if we have 3 plus 5 plus 2, right, and you're questioning, well, should I do 3 plus 5 first, right, and then get 8 plus 2 equals 10, or should I do 5 plus 2 first and then get 3 plus 7? Oh, look, that also equals 10. So the answer is it doesn't matter which 2 you do first, right? So the integers clearly satisfies condition 2 here. All right. The third one is the commutative property of addition, right? So this just means it doesn't matter what order you add 2 elements in, right? I should get the same result either way. Again, if you pick any 2 integers, 3 plus 5, this is obviously the same thing as 5 plus 3, right? So the integers are commutative under addition. So this is satisfied for the integers. The fourth criterion to be a ring is written here. I've used a bunch of fancy symbols, but this backwards E here just means there exists, okay? This 0R, this is what we're going to call the additive identity, okay? Because what this is saying here is there exists some element in the ring, which we're calling 0R, such that A plus 0R equals A for every element A in R, right? So for any element that you pick in the ring, if you add it to the 0 or to the 0 R here, you get that same element back, right? It doesn't change it. So 0 R here is called the additive identity. Basically, this fourth criterion just states every ring has to have an additive identity. Okay. Now the additive identity, the additive identity for the integers is just the number 0, right? 3 plus 0 equals 3. Negative 7 plus 0 equals negative 7, so on and so forth, right? This is, you know, more or less how 0 is defined, right? So it's not going to change. It's not going to change a number if you add 0 to it. 0 is the additive identity for the integers. Criterion 5 here says that every element in the ring has an additive inverse. Okay, what this means is pick any element in the ring, there must be another element in that ring such that if you add those two together, you get the additive identity. Okay, so for the integers, these are pretty straightforward. If I pick the number 3, well, we know there's also a number negative 3. And when I add 3 to negative 3, I get 0, right? Every integer has an additive inverse. Okay, so criterion 5 is satisfied for the integers, right? If, number 6 here, if we have two different elements, A and B, in the ring, then their product must be in the ring as well. Okay, so this is called closure under multiplication. It's basically the exact same idea as closure under addition up here, but you know, it just says that you cannot escape the ring through multiplication, right? If you take any two numbers and multiply them together, you get another result in the ring, another element of the ring. Okay, so just like with addition for the integers, this is true for multiplication of the integers, right? So if I take two elements, say 6 times 4, I get 24, which is another integer. And again, you know, you can prove that this is the case, but you know, for our purposes here, it's good enough just to see it intuitively that that works. So condition 6 is satisfied. Number 7. This is called the associative property of multiplication. So very similar to the associative property of addition, it just means it doesn't matter what, you know, if you have three things multiplied together in a row, it doesn't matter whether you do the last two first or the first two first, right? So this is definitely true of integers, right? If you have 3 times 5 times 4, right? And you might ask yourself, well, should I do the 5 times the 4 first or the 3 times the 5? The answer is it doesn't matter, right? We could say this is 15 times 4, which would get us 60, right? And if we did this part first, 3 times 20, which is also 60. All right, so this holds here. Okay, now the last one is the distributive property. Okay, and you probably saw this in your high school algebra classes as well. A times the sum of b plus c must be equal to a times b plus a times c. And then same thing if we have the sum come first, right? Then this c here can distribute to everything. This is obviously true for the integers as well, right? If we have, say, 3 times 4 plus 2, right? We could just say, oh, this is 3 times 6, which would get us 18, right? Or we could say this is 3 times 4 plus 3 times 2, which is 12 plus 6, which equals 18. So it works. We get the same thing either way. So the integers the set of integers satisfies all of these criterion. So it is therefore a ring. Now, there are a couple extra properties that rings often have that they don't necessarily have to have, right? This is the bare minimum to be a ring. But a lot of rings have other very useful and important properties. And you may have noticed that the integers, the set of integers also has some properties that are not listed here, right? So I'll call this extra. I'm going to write this down here, right? One extra thing that the integers has, which was not listed here, is that the set of integers isn't just commutative with respect to addition, but it's also commutative with respect to multiplication too. Okay, so that would be, AB equals BA for every A and B and R, right? Okay, if this is also true, then the ring is usually called a commutative ring. Okay, so not all rings have this property. A lot of them do. The integers has this property, right? It doesn't matter when you're talking about integers, it doesn't matter which order you multiply things in. For some other rings, like rings where the elements are all matrices, for matrix multiplication, you may remember, matrix multiplication is not generally commutative. So some rings may not have this property. We'll talk about those later. Another important property, which the integers also have, is the idea of a multiplicative identity. Okay, so we've already talked about the additive identity, right? But it's also possible for rings to have a multiplicative identity, right? So this property would look something like this. There exists, we usually call it a 1R, right, in the ring, such that A times 1R equals 1R times A, which just equals A. Okay, so in other words, this is the element which if you multiply any other element by it, it doesn't change, right? So for the integers, this multiplicative identity is just the number 1. Okay, so if you multiply 3 times 1, you get 3, not 1. Right? If you multiply negative 12 times 1, I'll just use that, right, then you get negative 12. Okay. If a ring has this property, it's often called a ring with identity or with an identity. This is the basic definition of a ring. Next time, we'll look at more examples of rings, including some that have these characteristics and some that don't, and we'll see some of the effects that these properties have on the way that rings behave. Thank you.